I've already mentioned to a couple of the students who were here earlier, and this Friday is a non-math day. It's an in-service training day for me, so I'll be at some virtual conferences, and so you won't be here at all. Your test 3 will still be on Monday. There's going to be a change to the homework schedule. Implicit differentiation will be the last topic for homework, so I'll move the other one to the following 2 weeks. And the test will be up to and including implicit, right? So this coming Monday, you know the routine. You get 1 more day, I guess, to study for the test and to get your homework over with. And I will be, so I'll still see you tomorrow, but on Friday I won't. So let's look at this fella. Who is the new topic? It's called implicit differentiation. An implicit formula is one that can technically be written in this format. The most likely implicit one that you've seen would be a circle. Now, technically speaking, a circle is not a function. And the reason it's not a function is because for certain values of x, aren't there actually 2 possible y coordinates on the curve? So it's a curve, but it's not a function. So we're looking at implicit curves and we want to differentiate them. So can you imagine any mixed up combination of x's and y's? Because that's what implicit expressions look like. You know, x squared y cubed plus the sine of y plus e, you know, whatever, right? X's and y's all jumbled up. And these are implicit expressions, and we're going to find out how to differentiate them. And the argument for why it's even possible to do that is kind of visual. Can you imagine I have an implicit curve and, you know, they swing round and they go back the way they came and they do all sorts of things. But if I pick a point P, would you agree at that point P there's a tangent line? And if there's a tangent line, it means it's got a slope, right? And if there is a slope of a tangent line, doesn't that mean that the derivative at P must exist? So we are going to be trying to find, or we will be finding, the derivative of implicit expressions. And it's not a formula like the product or quotient rule. It's much closer akin to the chain rule. It's a process rather than the formula. But in implicit differentiation, there isn't even a pseudo formula that I would write down that nobody uses. There is no formula for it. It's pure process. And we are going to find the expression for the derivative at the point P. And we could use y dashed, but I'm just going to use dy by dx. So we are going to find the derivative dy by dx of any implicit expression possible. So let's pretend that that point P is the guy I'm trying to find the derivative at, right? So how does the process work? It's actually, to write it down, it's quite short. There are only 2 steps, typically. Step 1 is you differentiate it. And step 2 is you isolate. You solve for, is another way of saying it, for dy by dx. Well, to get the step 1, the differentiation, we're going to have to go back a little bit. And I'm going to show you how you do the bits that it's made up from. So we break the job into little bits, and each little bit gets differentiated. Now, we always think of y as a function of x in these cases, and that's important. If I went and asked you to differentiate x cubed, you would use the power rule, I hope, and you would say, yeah, 3x squared. If I ask you to differentiate y cubed, think of it as something cubed. You get 3 something squared times the derivative of the something. So the derivative of y cubed is 3y squared times dy by dx. You see, it's very like the chain, right? It's something. The something just happens to be y. If I asked you to differentiate e to the y, the answer would be e to the y times dy by dx. If I asked you to differentiate the sine of y, the answer would be the cosine of y times dy by dx. Do you see that the theme is, it's pretty much the same thing that you would normally do, right? Differentiate, but with an extra dy by dx. So if you keep in your back of your mind, whenever I differentiate anything with a y in it, make sure that you finish with a times dy by dx, and you should be pretty safe. So you can do almost anything. If I wanted to differentiate e to the power of y cubed, you would get e to the power of y cubed times the derivative of y cubed, which is 3y squared, and you finish with the dy by dx. So from that basic idea that we can differentiate functions of y, right? Chain rules essentially, e to the y's and sine y cubes or whatever you want, by simply just following this process. That's then going to help us to do this guy. So step 1 is differentiate. And what you do is you differentiate each piece on its own. Right, if I differentiate x squared, it's still 2x, right? That's not changed. If I differentiate the number 25, would you agree that that's 0? Now, the only guy in town that's new is I need to also differentiate y squared. Now, bear in mind what we just said earlier. Don't you just differentiate it like it was something squared, right? Y squared. And what do you get when you do something squared? 2 somethings times the derivative of the something. So y squared gets me 2y dy by dx. Do you feel comfortable about that step? Now, step 2 is take this fella here and solve for dy by dx. Just like you're solving an equation. And what I mean by solving is isolate dy by dx and it's equal to everything else. So we're going to use a rule that I use a lot. I've got my own name for it. And the rule is, as long as you do it to both sides, it's okay rule. So we are going to take this guy and we are going to subtract 2x from both sides. What am I going to do to both sides next to isolate dy by dx? What should I do to both sides next?
Divide by 2y.
And like style points is everywhere. In this case, the style points were just cancelling out of 2. But can you imagine sometimes the style points might be factor out an x or factor out an e to the y or something, right? You know, make it look pretty as can be. Sometimes you get cancelling if you're really, really lucky, but it doesn't always happen. So for this circle, the slope of the tangent line is negative the x over the y. So let's pretend that point P had coordinates 3, 4. If I wanted to know the slope of that tangent line, wouldn't I just evaluate this at negative 3 over 4? So that guy has a slope of -3/4. Does that look right? Yeah, it's negative. It quite easily could be -3/4. So far, so good. I know it's only the first one, but what we're talking here is the process rather than the particular question, right? And the process is differentiate. Remembering that if there's a y involved, that when you differentiate, you get the same thing you normally would get, but finish with the dy by dx. That's step one. And then step two is whatever you have here, and it'll be all sorts of stuff, solve for dy by dx. And that's you finished. So let's try some polynomials. Yeah. I'm just scattering them all over the place, right? There's x's and, well, there's only one y location, but there are x's and y's all over the place, right? So it counts as implicit. Now, differentiate 3x squared. Differentiate 14x. If you differentiate that, you get nothing. If you differentiate 10x, you get 10, right? And the only guy that I really think we need to worry too much about is the 4y cubed guy, right? Okay, you want to differentiate 4y cubed. It's just like 4 somethings, right? So 4 something cubed, right? Just like the general. So you will get 12y squared and finish with a dy by dx. Are you happy with that? That the derivative of 4y cubed is 12y squared dy by dx. Now, my next goal is to eventually get dy by dx on its own. But that very rarely is a one-line deal, right? Depends on how ugly the thing is. My first strategy would be to subtract 10 from both sides and subtract 3x squared from both sides. Does that make sense? Just to get rid of these so that this guy is left. So I'm going to take away a 3x squared and a 10 from both sides. In the vast majority of these questions, you always finish with the divide. Can you see in this case, I'm going to finish with the divide. I'm going to divide both sides by 12y squared. Quick look to see if there's anything style point related. Nope, can't see anything. Call it good. So that's finished. Let's try this fella. Well, if you differentiate x squared, you get 2x. If you differentiate y cubed, you get 3y squared dy by dx. If you differentiate 3 sine y, you will get 3 cosine y times dy by dx. Do you notice that when you differentiate that and that, do you notice the dy by dx is at the end each time? If you differentiate anything with a y, remember to finish with the dy by dx. Now, if you differentiate the number 1, you get 0, so I won't use that. And if you differentiate an x, you get 1. So that's basically step 1 done. What about solving for y now? Yeah, I know I want dy by dx on its own, but you got to kind of do it in a particular order. So what do you think I'm going to do next?
Move the 2x over.
Okay, so subtract 2x from both sides. Once you get more comfortable with this, you can start combining some, you know, two lines of working into one line of working, right? Do two things at once. But I'm not going to do that. Too much happening. Yeah. Okay, what do you think you could do? Oops, lost a Y here. What do you think you could do on the left-hand side?
Figure out the derivative.
Yeah, as a common factor. Now, some of you might have went from this line straight to that line. Right, so when I'm saying you do two for one, that's what I'm talking about, where you took this line here and you subtracted to 2x, and while you were at it, you pulled out a common factor. So you kind of done two things at once. Nothing wrong with that as long as you're comfortable with it. Otherwise, do it one line at a time. Okay, we're pretty much finished. What do I do to both sides to get dy by dx?
Divide by 3y squared and 3 cosine y.
Yeah. And yeah, I'm being nitpicky for the next line. Style points tells me I probably should pull out a 3. In a test, I would let that slide. But in that case, because it's not that big a deal, would you agree 3 is just a common factor? But if it was a common factor at x, I would ding you, because x is, you know, or y or whatever it is a little bit more important as a common factor than just a 3 is. But it's good practice to do it anyway. That way you don't need to worry about, do I need to bother or do I not need to bother? Well, if you always do it, then you've got a rule you can stick to. And that's step 2 done. How are we doing? New guy in town, a new technique, implicit differentiation. Begin to feel a little bit more comfortable about it?
Seems okay so far.
So, yeah, good. So I'm just looking through some of the homework questions just to give me some ideas. I want to do one more like that, and then I want to do the product drill. So I'm seeing if I can find one more like that. This one I'll do. This is like question 6. So I have a sine of x plus a cosine of y, and it's equal to 5x, take it 8y. Okay. Differentiate sine x, you get cosine x. Differentiate cosine y. Okay, what do you get if you differentiate cosine y?
Negative sine times dy dx.
Yeah, as long as you remember that dy by dx, when you differentiate a thing with y in it, at least, you are fine. Right, differentiate 5x, you get 5. I don't know why this causes trouble, but people have problems with negative 8y or plus 4y, or, you know, some just with a y. What's the derivative of negative 8y?
8 dy over dx.
Yeah. Do you know what the mistake is? They lose the dy by dx. I don't know quite why they do that. Don't do it, because it's wrong, right? It is there, it should be there. I mean, that one didn't have it, this one did. You see, that's kind of asymmetric, isn't it? You would think symmetry, you know, they both would look the same, but they don't quite. I mean, look at that. They don't look the same either, don't they? When it's an x, you just get what you get. When it's a y, you get this dy by dx thing that keeps on getting tagged on. Now we got an algebra problem. We want to solve for dy by dx, right? That's our goal. dy by dx equals big ugly fraction. How am I going to make that happen? Because it's not going to be a one line. So just tell me one thing to do that's going to get closer to that answer. What could we do?
Would you move the -8 dy over dx to the left side?
Okay, and I'll do that by adding it to both sides. So I'm happy with that idea. In fact, I'll leave this guy on the left, right? Because I like that. What do you think I should do to the cosine x then, while we're at this?
Subtract it from both sides.
Right. Is it okay then that I've done both those at once, rather than write it down and then write another one, right? You know, nobody likes to write 5 lines when, 4 lines will do. I think this question's pretty much over with. Would you agree? Would you agree the next 2 steps are pretty much standard? So what's the next step then? What do I do next?
Factor out dy over dx.
And you will notice that in these questions, you tend to do factor out the dy by dx is the second line, and won't the last line be divide everybody by whatever this ugly mess is? Bingo. Can't do anything better. Call it good. Right, so we are now able to differentiate a fair number of implicit expressions, but not all of them yet. So we're going to now look at questions that need the product rule. So let's do x squared y cubed plus 3x to the 4 equals 4x minus 1. Now, if you differentiate 4x, you get 4. You differentiate the number, nothing happens. You differentiate this guy, it's a power rule. But x squared y cubed, it's 2 things multiplied together. That's why it's a product rule. And x squared is going to be the first function, and y cubed is going to be the second. So differentiate x squared, you get 2x, leave the second guy alone, plus first guy alone. And if you differentiate g, you get 3y squared times dy by dx. Are you happy about the product rule and the pieces that it was made from? The f dash g and the f and g dashed. F dash g, f g dashed. Right, at this point here, really, aren't we just going to do what we always do, try and solve for dy by dx? How about subtracting this guy and that guy from both sides? And while I'm at it, I'll rearrange this fella. Looking good. And divide. Looks like that. Do we have any style points that we could deal with here? Anything I could do to pretty this up a little bit?
Factor out a 2 from the top.
Yeah, I'm not going to bother because it's not a biggie. Would you agree it doesn't really help much? There are situations where it does. Okay, imagine I pulled out a 2 from the top and this guy in the bottom was 4x squared y squared. Wouldn't pulling that a 2 allow me to cancel it down a little bit? And that would be the exception to the rule where if it's only a number, don't worry too much about it, right? So if the common factor is a number, typically I'm not bothered about it. It's nice if you remember. But if the number that you're pulling out will actually simplify it, then you really do need to do it, right? So if that was 4x squared y squared, I would expect you to do that cancelling. Do another product rule. How about x squared e to the y plus y squared e to the x equals x? That's interesting kettle of fish. Because isn't that going to be a product rule? And isn't this going to be yet another product rule? So there are really 2 product rules happening here. And differentiate that guy, you get 1. So for this, I'm going to do an f dash g plus f of g dashed. And for this fella, I'm going to do another product rule. You start with this one. Differentiate x squared, you get 2x. Oops. Leave the other guy alone. Plus x squared. And when you differentiate e to the y, you get e to the y dy by dx. Now let's do this one. When you differentiate y squared, you get 2y dy by dx. Leave the other guy alone. And then leave y squared alone and differentiate e to the x. And the whole thing's equal to 1. Now when I look at this expression, I kind of see 2 different things. You see these 2 guys in the middle? I like them being together because they both have dy by dx's. But you see these 2 guys at the ends? I don't like them because I don't want them to be here anymore. I want them to be over on the right. So I'm going to subtract 2x e to the y and that guy from both sides. You comfortable about what I just did there? Subtracted this guy from both sides and this guy from both sides to get this and leave these 2 exactly where they were. And then we're going to finish with the last 2 lines, right? Pull out dy by dx and then divide. So if I pull out dy by dx as a common factor, I should plan my spacing a little bit better. And dy by dx is going to be all of this guy divided by that guy. And I can't see anything useful style points to do here. So I guess we're finished. Product rule. Any questions? Right. They're just getting uglier, right? Every question gets a little bit harder, a little bit uglier, right? More things to keep track of. Here's a different kind of product rule. Because this isn't just a product rule. This expression here is technically a chain rule followed by a product rule. And so that makes it a little bit harder. But let's take care of these guys first. If you differentiate y with respect to x, what do you get?
dy by dx.
Yeah. You don't get 1. Well, I guess you get 1 times dy by dx, but you don't get 1 on its own. Y squared, don't think we're going to have problems with that guy. We've done enough of those to get used to it. Uh-oh. I have this guy, the tan of x squared y cubed. Think of it as the tan of something, right? Think chain rule, tan of something, right? What is the derivative of a tan of something? It's one of your 6 guys. What's the derivative of a tan of something?
Secant squared.
Okay, so we're going to get the secant squared of something times the derivative of that something. And very often I write down what I'm going to do rather than do it, because it's too messy to try and do it all at once. Now, when I find the derivative of x squared y cubed, would you agree that that's going to be a product rule? X squared y cubed. When I find its derivative, it's going to be a product rule. So what I'm going to have is secant squared x squared y cubed. I'm going to call this guy f and this guy g. So when I differentiate it, I'm going to have to use the product rule on it. And then the rest, I'm just rewriting them again. That way, right? Let's see where we end up now. Okay, if you differentiate x squared, you get 2x, leave the second guy alone. Leave the first guy alone and differentiate y cubed, you get 3y squared dy by dx. You still have 2y dy by dx here, and it's still equal to a 1 dy by dx. Yeah. Okay, differentiation is now over. The algebra of solving for dy by dx is now about to begin. That is pretty much the ultimate of ugliness as far as product rules go. So if you can handle this one, there's nothing in the homework you won't be able to handle. So let's see how we could handle this. Any ideas for what my next line should look like? What should I do?
Distribute the secant squared.
Yeah, which for some of you might seem counterintuitive, but you know, sometimes you have to make something uglier before you can make it nicer. You just have to. So I'm going to multiply through these 2 guys with that fella. So hopefully I've got enough room for it. Secant squared times this guy gets you 2x y cubed, secant squared x squared y cubed, plus this guy and that guy gets you 3x squared y squared, secant squared x squared y cubed dy by dx. And then the other 2 guys are the same 2 guys untouched. Okay, we have 3 different places or terms that have dy by dx and 1 term that doesn't have a dy by dx. Okay, so where are we off to next?
You could get all the dy by dx terms on the same side and move that first term over to the right.
So I could move this guy over to the right and this guy over to the left, essentially.
Yeah.
Great. Okay, let's do that then. So I have 3x squared y squared secant squared x squared y cubed dy by dx. I have a 2y dy by dx, and if I take that away, I'll have a minus dy by dx, and the whole thing is going to be equal to negative 2x, that guy, secant squared of stuff I don't have enough room to put in, and then we're going to get dy by dx. And if you pull that out, you have 3x squared y squared secant squared x squared y cubed plus a 2y minus a 1, and it's equal to negative 2x y cubed secant squared of the guy I don't have enough room for. And won't dy by dx, and you are not allowed to do this, but I can, won't it be negative 2x y cubed secant squared, forgot what the darn thing is, x squared y cubed all over dot 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 dot, and dot 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 is all of that. I'm just being lazy. It doesn't take much to say that is as ugly an expression as you're likely to meet, and I don't see any style points in it. I don't see anything I can do to make it prettier. So we're stuck with it. Most of your questions are not going to be anywhere near as horrendous as that one. But at least you've seen one like that. But last question for today. We're going to look at a question that involves the quotient rule. And I'm going to pick the same one I chose with my other class because it's ugly. And you don't actually get that many of them. So if I do this one, I'm kind of, where is it hiding? Here it is, it's question 4. So we have x squared over x plus y equals y squared plus 7. First glance, would you agree quotient rules are kind of obvious? I mean, you see a fraction, you know you're going to do a quotient rule. And yeah, that's exactly what we're going to do. So the top is going to be f, the bottom is going to be g, and the quotient rule is f dash g, take away f of g dashed, all over g squared. And differentiate this guy, you get 2y dy by dx, and differentiate 7, you don't get anything. So here it goes. Top guy gets you 2x, leave the bottom guy alone, minus, leave the top guy alone. What do you get when you differentiate x plus y with respect to x? What's g dashed? What do you get if you differentiate this guy? Any takers?
1
Plus dy over dx.
Agreed. Are we getting a little bit more comfortable about if you differentiate a y? Remember, there's a dy by dx tagged on at the end, even when it's just y. Technically, it's 1 dy by dx. Oh, and the whole thing is over x plus y squared. Okay, so the next, whatever, 5 or so minutes, because it'll probably take us that long, is to figure out how we are eventually going to get dy by dx. So you're the first person in the universe, right? pretend you're the first person in the universe with this problem. So you got to figure out how it's going to happen. Any ideas? No, one little bit at a time.
I want to say multiply by the denominator.
Oh, so you want to multiply both sides by x plus y squared?
That's what I'm thinking.
Okay. That is a totally valid technique. It's not the only technique, but it works quite well. So, yeah. Don't knock it if it works. Would you agree that by doing that, you've now got rid of the ugly fraction problem? Because you know that fraction had to leave, right? It has to go somewhere. Are you happy about x plus y squared? Does that make sense? If you want to call it something over 1, can you think cross multiply? Maybe thinking that that way might make it a little bit more obvious. Right? Cross multiply with the 1 in the bottom. Okay, that's a good start. Let's move to the next phase then. What do you think we should do next?
Distribute.
Okay. 2x squared, 2xy, minus x squared, minus x squared, dy by dx equals x squared y. So 2x squared y, 2xy, 4xy squared, y squared plus 2y cubed dy by dx. Yeah, good thing to do. Where do we go next? Well, we're not far away from the end. Your ultimate goal is to get dy by dx on its own.
We can group the terms that have dy by dx.
Okay, so doesn't that mean this guy has to come over here? Probably.
Yep.
Right, so let's add it to both sides then. Oh, and while I'm at it, let's take care of those 2x squared. So I now have x squared plus 2xy, and it's going to equal all of this guy plus that guy. So what's that? 2x squared y plus 4xy squared plus 2y cubed plus an x squared dy by dx. Is it okay for me to add an x squared y, x squared dy by dx and put it inside here in one go rather than foiling the whole thing out just to put it back together again? Are you okay with that guy just popping in here? Does that make sense? Right, it's either a dy by dx, so we're essentially just adding an x squared to both sides. Right, we're done. One line and we are done. This line. What's the answer? Or what do I do to get the answer?
Divide by that 2x, y
Yeah.
over 2x squared.
So divide by that guy, I'm just going to call dot, dot, dot again, right? That's the guy I'm calling dot, 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 because I'm getting lazy now. Now that I've thought about it, I'll take it back. There's a style point, one that I wouldn't let slide.
Factor out the x.
Yeah. So it should be x over x plus 2y over big ugly mess. Now I'm happy. Just double check. Yeah, there's nothing in there. You know, the big ugly mess is just going to be a big ugly mess, right? I can't see anything to do with it. Are we good? Right, just to remind you, because I know some people turned up late, Friday is a non-school day. I'm going to be doing an in-service training. Thursday is a normal day. Our goal on Thursday is to finish doing some more implicit differentiation. That means that your test will be on Monday, as it was always going to be, and it will be up to and including implicit, but the next section